Okay, this is 4.1, investigating nonlinear relations. It's important first that we understand what we see as the independent variable and what we see as the dependent variable. So we did mention before this lesson that time is almost always the what? Independent or dependent? Nicholas?
Independent.
Independent, good. And as the independent variable, we always graph the independent variable on the x-axis. Independent. This could be time. And the dependent variable could be something such as height, so we're measuring height over a certain amount of time. So this is the y-axis. Okay, so specifically what we're looking at today in 4.1 is nonlinear relations. So we're accustomed to graphing and finding equations for linear relations, which are straight lines. So it can either be a straight line with a positive slope, with a negative slope, or even a slope of 0. All of these are different graphs that we're accustomed to graphing. We all have that standard equation of a line, y equals mx plus b, that we've gotten so used to seeing now. However, what we're looking at today is nonlinear relations. So a nonlinear relation is a relationship between two variables that does not follow a straight line when graphed. So we are still looking for a relation. So some sort of relationship between an independent variable and a dependent variable, however, doesn't follow a straight line. Okay, so if we were to do a scatter plot of the points, both the dependent and the independent, what we'd find is that we'd have this sort of relationship with a curve if we draw a line of best fit. So not a line straight through, but rather a line that we can see a noticeable change in direction as we start plotting those points. Okay, so that's what we're kind of interested in today. So the independent variable is the one you control before the trial begins. And it's always plotted on the x-axis. So that's a good way to think of it. So in science, when we do experiments where we're measuring, say, the height of a plant growth, okay, and we want to measure the height of that plant growth by, let's say, hours of sunlight. Okay, what would be the dependent variable, and what would be the independent variable in this case? Andy?
Hours.
The hours would be independent. Okay, and the height would be the dependent, because the height is what we're actually measuring throughout the trial goes. And the hours of sunlight, we can actually dictate how many hours that plant receives by using a light, right? We can turn on the light for a certain amount of time. We can turn off the light for a certain amount of time. So the light is the independent variable, whereas the height of the actual plant is the dependent variable. Okay, so the independent variable is the one you control before the trial begins. You plot on the x-axis. The dependent variable is the one you measure during the trial, and you plot on the y-axis. To determine if the graph is linear, look at the scattered plot. If line is curved, it's a nonlinear relation. So here again is that example I drew over there where we have a curve moving up. You could also have a curve going down, or any sort of curve. Okay? It could all be considered nonlinear relationship. Let's think of another example of dependent versus independent. How about do a little trick here. How about the number of hours that you've had sleep versus what level of grumpiness you are? Okay, not so straightforward. Again, we are dealing with time, but not as straightforward as kind of height versus time. Who can tell me? So I'm going to graph this now. Which one is independent and which one's dependent? Outer.
The time is independent?
Time is independent. So number of hours sleep is what we're determining. And then our level of grumpiness is what we're measuring. Does everyone agree with that?
Yep.
Yeah, so you would have, good, number of hours sleep down here. Grumpiness up here. Right? How about this one? Number So you say you're playing NHL 13 with your friends and you'd like to graph your number of goals scored versus the number of games that you've played. So you got to make a decision here. Which one you're going to put on the y-axis and which one you're going to put on the x-axis. What do you think, Jonathan?
Number of games played is the independent.
Good. Excellent. Why'd you say that?
Because it's the same as the time in the other one. Like games played would be referred to as time.
Sort of, yeah. Well, you're choosing the number of games that you decide to play, right? You get to choose that, and it's a set number, right? And then the number of goals is what you're actually measuring. So during the trial, so to speak. Luigi?
No, I was gonna say because it's like since it's a number of games played, you can't score goals without playing games. So, but you can play games without scoring goals. So.
Okay, good. Another way to look at it too is that the independent variable is always kind of a set difference, so to speak. So we're not going to have number of games played is going to be 1, 5, 10. It's always going to be 1, 2, 3, right? Like it's always a straight measure. Same as number of hours sleep. You can do it can be a kind of linear scale. Whereas the one that you're measuring on the y-axis can kind of go up and down, right? The independent variable never goes two directions, so to speak. After playing 5 games, you can't then play 4 games. You know, obviously you need to then play more games as you measure that independent variable. Okay? So I think hopefully that clears up any confusion you guys might have with independent variable and dependent variable. The rest of 4.1 is just a matter of graphing, so we all know how to graph 2 data points, an x coordinate and a y coordinate, and then tracing a line of best fit, and then determining whether that line is either linear or nonlinear. And that's based on basically the curvature of the line. Luigi?
You said that most of the time that time is independent. When would it be like the case when time is not independent?
Good question. Can anyone think of an example when time would not be? Yeah?
When you're comparing times.
Okay, like what would be an example? What would be two
How
time?
long it takes to drive to Montreal or take a train there?
Okay, that's a good one. Yeah, so the amount of time it takes to get somewhere. So say you were doing a study of how long it takes to get to work in the morning. Okay, so you have number of hours driven versus day of the week. Okay, so in this case, time is your dependent variable. Time is what you're measuring. So it took me 5 hours on Monday, or I should say 10 minutes on Monday. It took me 20 minutes on Tuesday. Thursday it took me 5 minutes. So you have this sort of graph. So here's your time on your y, and here's your day of the week. Okay? Or it doesn't have to be another measure of time. It doesn't have to be day of the week. It could be car model. Okay, so I'm using different cars to drive to work. On Monday I use a Ferrari. On Tuesday I used a Volkswagen. Okay, so we have different amounts of time it takes. Any other questions? Okay, that's a good one though. Number of hours driven versus day of the week or type of car driven. Okay, so the only last point I want to make for 4.1 is typically you will have a graph that looks like, you're going to have a graph, and because this is nonlinear relations, you're going to have a scatter plot. It looks something like this. This is 1, 2, 4. Okay, so we have a graph like this. You're going to plot this out in the homework. Then you're going to draw a line of best fit. So remember, a line of best fit goes through the most amount of points. Okay? We can see that this line is nonlinear because it has a curve to it, an obvious curve. And then the question might read, what would the value or the y value be at the x value of 12? So we don't have any points over here, so we can't just look at a particular point and line it up. But what we do have is what we do have is a curve. Okay, so we have this curve. So you're going to what's called extrapolate that curve. So you're going to kind of guess where that curve would go if you progressed in the x direction. Okay, you can see that it's leveled out at this point, so I can say confidently that the y value at 12 is still going to be around 4. Okay? In another example, you could have a curve that looks something like this. Okay, and then you have, say, 5, 10, 15 here. So this question might read, what would the x value be, or sorry, the y value be at x is 20? Okay, or how many people on this amount of buses, so to speak, where you have this exponential relation. So you need to determine when will y cross the x value of 20. So you need to extrapolate this curve. So you move it on up, it's going to hit somewhere up here. So I would guess around here, if you extrapolate this now, 50, 30, 45. Okay, so it would have a y value of 45 when the x value is 20. Does that make sense? Well, these graphs are a little messy, but you're just going to extrapolate the curve. So in other words, you extend the curve in the direction that it's already been going. Matthew?
Are some graphs going to have like a maximum capacities that we could reach? Like by using the bus example.
Yeah, I see what you mean. So if you had like a 40 out here, will this curve eventually narrow out enough to not touch the 40? Is that what you mean?
Well, yeah, that too, but eventually you can't fit 100 people on one bus.
You're right. So there was a kind of a bad example with the buses, but something that increases exponentially. Okay? It could be multiplying bacteria. All right? So when you have 5 bacteria, they multiply, you get 10 bacteria. Okay? But as those 10 multiply, now you have 30 bacteria, you're actually going to increase drastically. All right? So that would be maybe a better example of something increasing exponentially. It could be population growth. All right? Because bacteria tends to double. Yeah, Luigi?
When would you use it? Because like you can't really use it in real life situations because there's always like external things that could affect it.
When can you use what?
This guessing where it would go. Because there are always going to be like external things that would affect the way that the graph will go, right?
You're right, but you can use it to estimate, right? You're not going to necessarily be exactly right because, like you said, there's always external. But you can estimate, right? So for instance, if we did a graph like this, right, and we graph number of car accidents, right, and then we put on here month of the year. Okay, so we start off, we go January, February, March, all the way until December. I can say with somewhat certainty, okay, that around the months of January, December, February, Maybe a little bit lower in March, April, May, June, July, August, September, October. My graph's going to go something like this. Why do you think I know that? Okay, besides actually getting the data, what do I know it's going to look like that, at least in Canada? Yeah, Nicholas?
Because there's a lot of snow in the winter.
Yeah, because in the cold weather, we're going to have more accidents, right? So now if this is 2013, Luigi, in 2014, can I sort of extrapolate this into a similar type of curve?
Somewhat, but would never be certain.
Right, you're right. You would never be certain, but you can almost be certain that in January you're going to have more accidents than July for 2014. Would you not agree?
Yeah.
Just based on the road conditions, right? So the idea of this sort of extrapolation is to estimate, right? It's to make estimates. Because if I had a virus outbreak, let's say, right, and if any of you guys seen the movie Contagion, one of the things they need to know is how much time do we have? How much time before everybody's infected? And that's exactly what this type of extrapolation tells us is, well, if the virus is increasing at this rate, it's not a straight line. Definitely it's not, because as more people get infected, they infect more people. So it becomes this curved line, this kind of exponential line like this. They need to know, well, how long before everybody's infected? Well, if we take this curve and we extrapolate it, well, we know we only have about 3 weeks before, I don't know, let's say the entire world is infected with this, this crazy virus. So it's that type of information that we gain through extrapolation. Okay? And you're right, there are external factors. You're not going to know exactly, but you will get an idea. Okay? Yeah?
Is there a way to do it algebraically?
Algebraically? No. That's exactly Luigi's point. There's not, because we can't predict the future. So whenever we're going into the future, we can only kind of extrapolate graphs. Okay? There is a way to model this graph algebraically, and then saying if it continues on this exact curvature, we can tell where it will be. Okay? But in these particular problems where we're sort of extrapolating, we're guessing the factors, you can't never really be exact, just to his point. Yeah.
So is this what people do when they try bet on horses and stuff like that?
Maybe. Yeah, I'm not sure if they use mathematics like this, but it's possible. Yeah, okay, you can end it there.